Hello and welcome back to Gaffy's Grinds. My name is Mr. Gaffy and I am a Leaving Cert chemistry teacher. And in these videos, we'll be taking concepts from Leaving Cert chemistry, breaking them down, making them simple, and giving you practice to do to make sure you master the content. This is video 4 in our series on trends of the periodic table. So today's video is about electronegativity. We have previously looked at trends of atomic radius and trends of first ionization energy. And some of that stuff is pretty important to help you understand what we're doing today. So if you haven't already watched videos 1 to 3, then some of this is probably not going to make much sense to you. So I do suggest that you go and watch those other videos first. Let's consider we've got two hydrogen atoms. And I'm drawing a line between them. Sorry, I'll try and draw it a bit straighter than that. Drawing a line between them. And we don't normally draw this, but what this line represents when you see a line between two atoms like this is it represents, this is a covalent bond. Covalent bond. And what a covalent bond is it's a shared pair of electrons between the two atoms, and the two atoms are attracted to the electrons. That's what keeps them together. Now, electrons are equally shared between these two atoms. Why is this? Well, if we take a closer look and we were to draw, say, this atom of hydrogen and this atom of hydrogen, and inside these atoms, I'm going to put what we call the nuclear charge. Now, the nuclear charge is caused by the charge inside the nucleus. And the charge inside the nucleus is determined by how many protons there are. So in each of the nucleuses of hydrogen, there are 1 proton. That means each of these protons has a charge of +1. Now, if I refer to this bond again, remember that this bond is a shared pair of electrons, and electrons are negatively charged. Each of these is negatively charged. And what do opposite charges do? On 3, 1, 2, 3, speak your answer to the screen. Opposite charges attract, which means that the electrons are going to be attracted to the positive charge of the nucleus. But they are also attracted to the positive charge of this nucleus. Now, so just to recap, +1 is what we call the nuclear charge. And it comes from the amount of protons in the nucleus, so the nuclear charge. Now, because both of the atoms are the same, each atom has this has a +1 charge, the same charge. We call this attraction of the electrons for the nucleus. We call this attraction between the electrons, the negatively charged electrons, and the positively charged nucleus. We call this the affinity. We say that these oppositely charged things have an affinity for each other. So affinity just means that they like or are attracted to each other. So the electrons and the protons, or the electrons and the nucleus, have an affinity for each other. Now, because the nuclear charge of both of these atoms is the exact same, that means that the electrons on average are found right in the middle between the two atoms. So they are found in the middle. So the average position of the electrons is, sorry, spell it right, of the electrons is right in the center in between two atoms. We say they are shared equally because neither atom has a greater affinity for the shared pair of electrons. And this is because the atoms are the exact same. However, what if we consider two different atoms? So we'll take the example, a hydrogen atom, but this time it's bonded to a chlorine, like this, Cl. Is the above still true then? Do both of these atoms have the same affinity for the shared pair of electrons? This molecule is what we call hydrogen chloride. And before we are able to answer this, we're going to quickly do some practice questions, which are some retrieval or revision questions of previous topics, which are going to help us to answer this question. So what I want you to do, I've got 4 questions on the screen, is I want you to pause the video, get your periodic table, and answer these questions, please. Okay, so you should have paused, and you should only be watching the video if you and listening to my voice if you've done the questions. If you haven't, pause the video and do the questions now. Okay, it's like I always say, if you're not going to do the questions, you're really wasting your time watching this video. Okay, so let's go check the answers. Here they are. All right, so hydrogen, 1 proton in the nucleus, chlorine 17. We know this from the atomic numbers. Chlorine is going to have a greater affinity for the electrons because it's got a higher nuclear charge. Okay, so number 3, which atom has a higher nuclear charge? That would be chlorine. And number 4, which atom would have a higher affinity for the electrons? Or the shared electrons have a greater affinity for the chlorine atom. So, see how that was all relevant. Well, if we were to draw the atoms just like I did before, I'll draw the atom of chlorine under chlorine. This time I would have to write 17 positive in here because this is 17 protons, 17 protons in the nucleus of chlorine. Hydrogen is the same as the example above. It's only 1 plus or plus 1 because it's only got 1 electron or 1 proton, sorry, in the nucleus. I'm drawing the bond and I'm drawing the shared pair of electrons. So the shared pair of electrons is in here. Well, if I was to use the arrows again to show the affinity, we know that the affinity that they have for the plus 17 nucleus, the chlorine nucleus, is going to be much greater than the affinity they have for the plus 1 nucleus. This means that essentially the electron's average position is going to be closer to the chlorines. So we would show that like this. So let's draw out HCl again. If we were to draw the bond, the electron's average position is probably more like somewhere around here. They spend their time closer to the chlorine. Now, we can show this using this symbol here, delta, which is kind of like the square root symbol, but it's got a curl on the bottom. Delta negative. The chlorine is delta negative, and this delta, so I'm just going to label this now. This is what we call delta, D-E-L-T-A. It's a Greek symbol or a Greek letter, delta, and this is delta negative. And what delta means is partial. So this atom, chlorine, is now delta negative or partially negative. And the reason for this is because the electrons in a bond spend more time closer to it than they do to the hydrogen. So it's not a full Cl minus ion because that would mean it's fully removed electrons from hydrogen. So Cl minus ion would be fully removed electrons. So it's not fully removed the electrons from hydrogen, but it has a greater share of them. And we show this with this symbol delta positive. Now, or delta negative, sorry. If chlorine is delta negative, that must mean that hydrogen is now delta positive because it has essentially lost its share of that pair of electrons. So it's almost completely lost it. So this is delta positive. This is more positively charged because it's most of the time the electrons are spending time over the chlorine. So that's what we mean by delta positive, delta negative. They show partial charges. And what this does, okay, so before I go there, okay, we now basically have an idea that we can have these two atoms that have a different amount of attraction for the shared pair of electrons. So I'm just going to write about this now. So say we have something, if we're talking about the relative attraction, because remember, it's compared to each other, that's relative to each other, the relative attraction an atom has for a shared pair of electrons in a covalent bond. That's what we've been talking about. So we've got a covalent bond. When we put two atoms together, we compare them, we talk about the relative attraction each atom has for a shared pair of electrons in the covalent bond. This here is called the electronegativity. Each atom has an electronegativity, an attraction for the shared pair of electrons, electronegativity. And we can find the values for these electronegativities on this table. Now, if you guys are in Leave and Cert chemistry, you will find this table in your log tables. So in your mathematical and formula tables that you're always given in your exam, or you can ask for them, it has this periodic table in there. It's got 3 periodic tables. It's got a standard one with just the atomic and mass numbers with the elements. Then it's got one for first ionization energies listed on it. And then it's got this one, which is electronegativities listed on it. This here uses something called a Pauling scale to rank atoms or elements based on their electronegativities. The scale goes from 0 to 4, with 4 being the most electronegative and 0 being least electronegative. Least. So 4 is most, 0 is least. And obviously, anywhere in between that, we go up 0, 1, 2, 3, we're increasing electronegativities. Okay, and basically that means that the more electronegative ones will always attract the electrons to themselves more than a less electronegative. Okay, so this is what we call the Pauling scale, and it's named after the person who discovered it. Something to point out, no, I'll do that later. Okay, so that's electronegativity. It's the relative attraction an atom has for a shared pair of electrons in a covalent bond. Now, why is it relative? I want to highlight this word. Some people always forget to write this word in, the relative attraction. Well, here, if I asked you, how electronegative is chlorine? Well, in this example here, it looks like it's very electronegative. The electrons are spending very much attracted to the chlorine. But we can't just say chlorine is very electronegative, because if we compare it to something like fluorine, if chlorine was in a bond with fluorine, here you see them here. Now chlorine is the less electronegative and fluorine is more electronegative. So in the example above, it was right to say that chlorine is very electronegative, but that's very electronegative relative to the hydrogen. If it's paired with something else in a bond, it might not be very electronegative. So that's why this word is important, relative attraction. Now, when this happens, we create 2 areas in a bond that basically have opposite kind of ends to them, okay? The electrons are being unequally shared here, and we create something called a dipole, what we call a dipole. Now, this word comes from di, meaning 2, and pole, meaning opposite areas or opposite ends. It's kind of like a magnet. The way a magnet has 2 poles, the north and south pole, these are oppositely charged ends or oppositely charged areas. So opposite areas. So a dipole is like this here, where we get oppositely charged areas or slightly oppositely charged areas, and they are separate. We show this like this, using this symbol here. So it's like, I always like to think of this end of it as being a plus, and it's always on the end, it's delta positive. And then the arrow on the other end shows you the direction that the electrons have moved. Okay, so the electrons will move towards the delta negative end and leave a positive end behind. So this type of arrow here shows a dipole. So that is how we would describe a dipole. Okay, and when we have a dipole, what we have is we have a bond. We have a bond where electrons are unequally shared. Unequally shared. They belong, or they spend more time closer to one atom, which is the more electronegative atom, than the other atom, which is the less electronegative atom. So bonds where electrons are unequally shared, we call this type of bond a polar, because we're creating poles. It's still covalent because electrons are still being shared bond. So a polar covalent bond is a bond where electrons are being unequally shared. Time to do some practice questions. Okay. What I would get you to do before we do that is just take a note of these two definitions. These are definitions that can be asked in the exam. If you need to, you can take you can record the diagrams I have as well, but I mean, I've drawn them to help you guys understand as I'm explaining. I'm hoping that the explanations are clear. It's not, these videos aren't about copying down everything I say. They're about listening, understanding, and then practicing to apply the information. And that's what helps you to learn it properly. Okay, so do take down the definitions, just have a list because they do have to be learned pretty much word for word. Okay, right, time to do some practice questions. Here they are. So we are going to pause the video and try to do these 5 questions for me now, please. Okay, so you should only be listening to my voice if you have tried to do these 5 questions. Coming up are the answers. Okay. So 1 and 2 are pretty straightforward, I hope. It was just a definition in number 2, and in number 1 you had to recognize because they're the same atom, they have the same nuclear charge and they have the same affinity. How do we represent? Number 3 said in a water molecule, an atom is bonded to an oxygen atom is bonded to a hydrogen atom. The oxygen molecule has sorry, that should say atom. Sorry, the oxygen atom has a higher affinity for the shared pair of electrons and pulls the electron closer to itself. What signs can we use to show this? So what I was looking for here was delta positive and delta negative, and this is how we would draw it. So if it didn't have some kind of a drawing to show the bond like that, it'd be a good idea to do that now. Okay, so make sure that the delta symbol, I'll show you again, it looks like it's like the square root one. So instead of like that for a square root, you have curled in at the bottom like that. So that's the delta sign. Okay, delta positive and delta negative. All right, next question. In the above question, a dipole is formed. What is a dipole and how can we show it? Okay, so a dipole is where there are 2 oppositely charged areas. That would be explaining what a dipole is. And how can we show it? We can show it using this symbol here. Okay, so we show this is at the positive end and this is at the negative end, pointing towards where the electrons are moving. Next one, the above is an example of a polar covalent bond. What is sorry, that's not very clear. What is a polar covalent bond? Sorry, if that wasn't clear. The question is, what is a polar covalent bond? Apologies about that. So pause the video now and try and answer that question, please. What is a polar covalent bond? All right, so this is what you should have. A polar covalent bond is a bond where the pair of electrons is shared unequally, and it's because it's attracted to the more electronegative atom. So whichever atom is more electronegative on the Pauling scale will attract the electrons more than the other one. Okay. All right, so hopefully we now understand what we mean by electronegativity and what the result is. We get polar covalent bonds, and that's really important for lots of other things, but we won't go into that just today. We will look at it in other videos when we do bonding. But what's important now is that we're going to consider this table again, and we're going to look at the reasons why different atoms have different electronegativity. So why do these atoms have different values? So first of all, we're going to look at why, and then we're going to look at the patterns. Okay, right. So why do electrons have different electronegativities? So there are a couple of factors that are going to contribute to this. First of all, consider these 2 atoms. In one atom, we've got an atom of lithium. Lithium has 3 positive charges. So its nuclear charge is +3. We've already looked at a chlorine atom, so I won't use chlorine again. Let's say, for example, we take oxygen. This is lithium. And consider now for oxygen. Oxygen atom has 8 protons, 8p. This is oxygen. We say oxygen has a nuclear charge of 8. Oh, sorry, I shouldn't be saying 8p here. That's proton, but of course we're using the plus sign, 8 plus. So obviously oxygen has a greater nuclear charge than lithium. Now, all other things being equal, if these are put into a covalent bond where the electrons are being shared, well, which one is going to attract the electrons more? Or which one is going to have a greater affinity for the electrons? On 3, speak your answer. 1, 2, 3. It really is this simple. The oxygen, I'm hoping you realized, is going to have a greater affinity for the electrons. So relative to the oxygen, the lithium has a lower affinity shown by the shorter arrows. Oxygen has a greater affinity shown by the longer arrows. So obviously, the bigger the nuclear charge means bigger electronegativity. And obviously the opposite is also true. A smaller nuclear charge is going to result in a lower electronegativity. Now, these aren't the only factors though. The nuclear charge is not the only factor. It is one of the factors, but it is not the only factor. We have to combine a couple of factors to get the full reason why electronegativities change. The number of protons is definitely one of the factors. Another factor though, if we consider, is if we take 2 atoms, okay, let's take this atom here. Let's say it has we won't say how many protons it has, it's just got a positive nucleus. And the shared pair of electrons is drawn here, like this. Now, the shared pair of electrons is attracted to the positive nucleus. It has an affinity for the positive nucleus. Let's consider a second atom in the same situation. It's got a covalent bond, but this time the atom has a much bigger radius. The atomic radius is much bigger. We know that the positive nucleus is in the center of the atom, where the nucleus is. So the nuclear charge is in the center. Now, hopefully you can see that when we increase the atomic radius like this, we increase the distance of the nucleus away from the electrons. So this is further away. The distance is further. Okay. Now, actually, I'm going to undo some of these arrows because I don't want to confuse people. There's something you might be confused about here. All right. So let's say we're not actually talking about, when I drew the arrows before, I made it seem like the arrows were the size of the charge. So that there, if that's the size of the charge, and now from there to there is the size of the charge, it looks like the one below has a bigger attraction, and that is not the case. What we're actually trying to show here is not the charge, but the distance between the electrons and the positive nucleus. So I'm going to show using a completely different arrow than I have so far. I'm going to use a blue arrow. So here, the distance here is small. The distance here from the electrons to the nucleus is bigger. It's a bigger distance. That makes it harder for the nucleus here in the second one to attract the electrons because the positive charge is further away from these negatively charged electrons. So we call this the atomic radius. So when we have a smaller radius, in other words, the atoms are smaller, the electronegativity will be higher. greater, because the distance between the electrons and the positively charged nucleus is smaller. It means electronegativity is greater. When we increase the radius, that means the electronegativity gets smaller, like in the second example. Now, this is going to be really important when we start moving around the periodic table and we're starting to figure out, okay, why is it smaller there? Why is it bigger there? So we have to apply these factors to the periodic table afterwards. So we've got two factors that affect electronegativity. First of all, we have the nuclear charge. Secondly, we have the atomic radius. The third one I want to consider is if we take two atoms, and we know that, again, the two electrons are going to be attracted to the positive nucleus. Now, say this atom here, this is atom A, and in atom B, we have an atomic radius again, which is similar, and we've got negative electrons. But this one has an extra shell of electrons inside. Okay. There should be 8 electrons there, so I think there's about 8 there now. Okay, we're going to show, again, the affinity between the negative electrons and the nucleus. Here is the electrons being attracted towards the positive nucleus. Now, in this case, the electrons are still going to be attracted to the positive nucleus. But because the electrons here are negatively charged, and the electrons in this inside shell are negatively charged, shown in green, they actually are going to repel these electrons in the bonding pair. We call this green arrow here the screening effect, and we've seen this in previous videos. Screening effect. The screening effect is the third factor that's going to affect electronegativity. So, lower screening effect, lower screening means, well, what's the result going to be? You tell me on 3. 1, 2, 3. Speak your answer to the screen. Lower screening, I hope you said, means higher electronegativity. Negativity. And obviously, the opposite is true. Higher screening means lower electronegativity. Now we've got to put these 3 factors together: screening, atomic radius, nuclear charge, put them together and help us understand the numbers in the Pauling scale. All right, let's take a look. Here is the periodic table. Generally, when we're looking at the periodic table, we're interested in 2 particular patterns. One of them is what happens when we go down a group, and the way you're going to see this sometimes written in questions is descend. If you descend the group, it means you go down. Descend. How do you spell that? D-E-C-E-N-D, I think. Maybe there's an S in there. I'm not sure. Apologies. Descend the group, or when you move across the group, we're talking about from left to right. So we call this a cross. Okay. Now, you don't have to actually learn these numbers because you're always going to be given these, you're going to be given an electronegativity value table in your log table. So you don't have to learn the numbers or learn the patterns, but you have to learn to be able to think about, look at the numbers and think, always be able to think to yourself, why is that again? Work it out, okay? You have to be able to do that using the factors that we just talked about below. So let's look at the general trend, and you're generally asked to describe the trend, and then you're asked to account for it, which means if you're asked to account for it, you're using the factors we talked about below to explain why. Okay, so as we descend the group, let's take a look. It's always good to start with, ignore this one, okay, and start with group 1. Now, why am I saying ignore hydrogen? Well, hydrogen doesn't really belong to group 1. So let's just start with group 1, and all the others are going to follow a similar trend. Okay, but group 1 is a good place to start. Let's see what happens. Lithium is 0.98. Let's go to the bottom. Francium is 0.7. That tells me, so lithium, just clarify where they are. Lithium is here, 0.98. Francium is down here, 0.7. So there's a general trend that it goes down. 0.98 down to 0.7 is decreasing. Now, I'm just going to write here, it decreases. Now let's just check that it is a pattern, that it's not just, I've just taken those two and seen, all right, it went down, so the rest of them must go down as well. Let's check a pattern. 0.98, 0.93, 0.82, 0.82, 0.79, 0.7. Yeah, it is a pattern. Okay, so it goes down each time. It's a pretty good pattern. So it decreases. So if I was to ask to describe what happens to electronegativities down a group, I would say as we move down the group, group 1 or group 2, you can choose a group if you like to illustrate it, electronegativity values decrease. Right, so that would be stating the trend or describing the trend. Let's look at the trend across the table, across a period. So I'm going to choose period 2, this one here, and let's explain. All right, I'm going to get rid of that because it's messy, but yeah, that's what you get the idea. Right, so it starts lithium 0.98, fluorine 3.98. So I would say the trend or the pattern is it increases. So across the table, it increases. Now, note helium, argon, and neon. There is no values on the Pauling scale for electronegativities for these three elements, krypton as well. So why is that? Well, the reason for that is they don't do any bonding. So if they don't do any bonding, then you can't actually measure you can't measure what their electronegativity is. They don't have affinity for electrons. And this is because they have what we call the noble gas electron configuration, and they are highly stable. So we do not observe them bonding with anything else. So they are not going to attract electrons in a shared pair because they just don't share pairs with anybody. They've already got a stable configuration. They just don't participate in bonding. So we can almost exclude them from electronegativity and just go from lithium over to fluorine. And there's obviously a big increase there. So now we've stated the actual patterns. It would be important then to be able to describe and explain why each of those patterns is seen. So let's just summarize. So electronegativity values, what do they do? So I often shorten electronegativity to EN. You should do this in your notes, but not in the exam. EN stands for electronegativity. Right, so down a group, what happens? Electronegativity values, they decrease down a group. Decrease down a group. Okay, what are the main reasons for this? Well, the main reasons, well, what else is happening? What's happening to these other factors as we move down a group? Well, we saw previously that as we move down a group, say group 1, the atom gets bigger. So they decrease down a group. Why? Well, the first reason is atomic radius increases. The atomic radius increases. And what this means is that the nuclear charge in these atoms is further from the shared pair. So when the atoms get bigger, it's like this up here where we did here. Okay, so when the atom gets bigger, there's a bigger distance between the nucleus and the shared pair. When the atom is smaller, the distance is small, and the effect is that the electronegativity is higher. The nucleus pulls the electrons more strongly. So that's reason number 1. Factor number 2 is this guy. As we move down the group, we go through the energy levels, n equal to 1, n equal to 2, n equal to 3. So that's what happens as we move down the group. We add inner energy levels full of electrons, or what we call inner shells, which this has the effect of increase screening. Okay, increase screening. And the effect of this is that it basically starts to repel the shared pair of electrons. So although the nuclear charge is trying to pull them closer, the shielding electrons in the inner shells repel them. So essentially, they reduce. So the screening reduces the pull of the nucleus on the shared pair. Okay, so reduces the pull of the nucleus on the shared pair by shielding or repelling the shared pair of electrons. So that is what happens going down a group. What happens going across a group? Well, we've said the general trend is that electronegativity increases across a group. Okay, so why does it increase going across a group? Let's just double check that it does. Up here, look at group across a period. Sorry, I'm saying across a group. I shouldn't be. Across a period, say period 2 here, starts at lithium 0.98 and ends at fluorine 3.98. If we look at each one, there is a steady increase. So it's definitely a pattern. Okay, so we can definitely say, and like I said, you will always be given those values. So you can always figure out the general trend by looking, and then you have to think about why. Reason number one is, well, what's happening to the radius? Because we move across the table, what happens to the radius? You tell me. So 1, 3, think about it. Have a think, what happens to atomic radius across a group in the periodic table? 1, 2, 3, speak your answer now. Okay, so atomic radius, hoping you said decreases. So the atoms get smaller across a group. So atomic radius decreases. This has the effect of getting the shared pair to be closer to the nucleus, increasing the electronegativity. Okay. Number 2 then, what's the other thing? Well, as we move across the group, we are adding more protons, which means we're increasing the nuclear charge. We're increasing the nuclear charge without adding any extra energy levels. So we say that the effective nuclear charge is increased. So this word effective nuclear charge refers to basically the nuclear charge take away the shielding effect or the screening effect. So when we go across a table, we're adding more protons, but no extra energy levels full of electrons. So the effective nuclear charge is getting bigger because you're getting more positive charges, but you're not adding any inner shells to screen the positive charges. So we call this the effective nuclear charge. So we increase the effective nuclear charge, and this obviously increases the pull of the nucleus on the shared pair of electrons. That is the pull of the nucleus on the shared pair of electrons. That is the electronegativity. So very quickly, let's recap. Electronegativity, the pattern is it decreases down a group. Why? The atomic radius is getting bigger. That means that the nucleus of these atoms is getting further from the shared pair, so the pulling power is reducing, which means electronegativity values are going down. What else is happening? We are adding shells of electrons, inner shells, which increase the screening. So this again reduces the overall pull of the nucleus on the shared pair of electrons. So these are two reasons why the electronegativity of atoms reduces as we go down a group. What about across a period? Well, it increases across a period because the atomic radius decreases. In other words, atoms get smaller, which puts the nucleus of these atoms closer to the shared pair, which means they are greater at attracting the shared pair. We also have an increase in effective nuclear charge. The number of protons is increasing without any change in the screening effect because we are not adding any extra inner shells, which means the screening effect, the effective nuclear charge is increasing. Right, time to practice now and make sure that we have understood and that we commit this stuff to our long-term memory. Okay, so I've got here 7 questions for you. to practice. In question 1, part A and B, you just have to describe, not account for. So describe. C, which element is the most electronegative? So you will need an electronegativity or a Pauling scale for this. And then lastly, which factors must affect electronegativity, given your answers to A and B. So you need to describe the factors that affect electronegativity. Number 2 then is a recap of first ionization. Number 3 and 4 are explaining some pretty straightforward stuff, I'm hoping. Yeah, so you should be able to manage the rest of that. So I want to pause the video and do them questions now, please. All right, so showing me listen to my voice. If you have paused and done questions 1 to 7, let's check, see how you got on. You should be correcting this now with a red pen. So you should be either ticking it if you got it right. If you said the same thing, tick it. If you didn't, if you're not happy with your answer, then you need to add to it, fix it now. Okay, so the general trends, electronegativity increases across a period and decreases down a group. That's describing the general trends. Fluorine is the most electronegative. It's got electronegativity of 3.98. It's the most electronegative. Some electronegativity tables show it as 4. They just round it to 4, which is okay. D, what are the factors? The factors are a smaller atomic radius means higher electronegativity. A larger atomic radius means lower electronegativity. Okay, so you should have mentioned both of those. So smaller atomic radius. So we're focusing on, in the first bit, on the atomic radius. So we're focusing on the atomic radius in the first bit. Atomic radius and atomic radius. We're then focusing on nuclear charge. So if you didn't include nuclear charge in your answer, you should pause the video and do that now. Okay, so if you didn't include nuclear charge, you should pause the video and do that now. And then you should discuss also screening. So the 3 factors you should discuss if you weren't able to get them first time are atomic radius, nuclear charge, and screening. All right, so you should be playing the video if you have completed that question. Part D was probably the most challenging question here. Okay, so higher nuclear charge means higher electronegativity. More protons means more attraction or more affinity for the nucleus. Lower nuclear charge means lower electronegativity, because less positive charge in the nucleus is a lower affinity for electrons. The screening effect then is the next one. If we have inner shells of electrons, they will screen the nuclear charge. We get a larger screening effect, means lower electronegativity, and a smaller screening effect means a larger electronegativity. First ionization then, you can go ahead and correct that one yourself. That's just revision, so do that now. Correct it, either tick it or fix it. Number 3 then asks us to compare, explain why based on its structure, oxygen is more electronegative than lithium. So we should have referred to its structure. Oxygen has a higher nuclear charge, so you should have nuclear charge in your answer because it's got 8 protons versus lithium's 3. Oxygen also has a smaller atomic radius and no increased screening. We know this because we're moving from left to right across the periodic table, and the atomic radius is decreasing, the atom is getting smaller. So they're in the same period, oxygen and lithium, and oxygen is further to the right, which means that it is a smaller atom, and there is no increased screening. We have not added any extra shells of electrons. So that is a good explanation accounting for why oxygen has a lower electronegativity than lithium. What about this one? Explain why oxygen has a greater electronegativity than sulfur despite having less protons. So if we take a look at our table Pauling scale again, here we see oxygen is right above sulfur in the periodic table, and oxygen's electronegativity is higher. So what are the reasons for this? Well, oxygen has a smaller atom. It's above it in the periodic table. It has less shells, so it has lower amount of energy levels, which means it's got less screening, and it's got a smaller atomic radius. So even though it has less protons, it's the other factors are much more important here. We've got a smaller atomic radius and we've got less screening. So that's what we should have said. Let's go back to the answer over here, the written answer. Sorry. Here. Yeah, so here oxygen has fewer protons than sulfur. This is true, but it has a much lower screening effect because oxygen has only one inside shell and that is just the first shell with just the 2 electrons in it. Sulfur has that first shell with 2 electrons, but it's also got a second full shell with 8 electrons, so a much bigger screening effect. And it's also a smaller atom. Sorry, I haven't mentioned that here. It's also a smaller atomic radius. Smaller radius. Okay, you should mention that also in your answer. It's got a smaller radius. N2, explain why N2 is not an example of a polar covalent bond. Well, of course, N2 has 2 ends bonded, and these are the same atoms, so they will have the same electronegativity, which means the electrons will be shared equally. So it's not polar covalent because the 2 atoms have the same amount of protons in the nucleus, basically, same atoms. So what have I said? N2 is not polar covalent because the 2 atoms have the same electronegativity and the electrons are equally shared. So they are identical atoms, same electronegativity. They don't attract more than the other one. The electrons are equally shared. What about HF? Why is HF an example of a polar covalent bond? Well, HF is polar covalent because fluorine is much more electronegative than hydrogen. Let's go check that out. One more time over to the table. Let's go check it out. We've got fluorine, which has an electronegativity of 3.98. And we've got hydrogen, which I need to clean up over here, has an electronegativity of 2.2. So you see there, that's quite a difference. That's a difference of 1.78 about. So that's quite polar. That means fluorine has a much higher affinity for the electrons than hydrogen does. So HF is polar covalent because fluorine is much more electronegative than hydrogen, creating a dipole, what we call a dipole, because electrons are shared unevenly. So you should definitely have the word dipole in your answer. You should definitely mention this phrase, electrons are shared unevenly. And then lastly, why are no electronegativity values for helium, neon, and argon included in the Pauling scale? And this is because they do not form any bonds. So if they do not form any covalent bonds, and that's because they're highly stable, then you can't measure any electronegativities. They don't have any affinity for electrons in a covalent bond if they don't make any bonds. So they do not form any bonds because they are highly stable. So you should mention highly stable, and you should mention no bonds or don't form any bonds. Okay, all right. That is electronegativity and the trends and patterns as we move around the table. So in the next lesson, we are going to look at some more patterns in the table. These are the 3 main ones that are on our course though. These are the 3 main things you get asked about, and we can be asked these get asked quite often, pretty much every year in some form or other. So that's it, guys. If you found this useful, if you really think it helped you understand electronegativity trends around the periodic table, especially if you found, doing the questions and getting more practice than you might in another video. If you found it useful, guys, please do give it a like. Helps other students find it, and it might mean someone else can get help from the videos. Also, if you have any comments or if you want me to do any particular topic for you guys, do leave a comment down below and let me know so I can put one together. Thanks, guys. See you in the next video.